again, welcome to another session here, and I'm very happy to be able to introduce William Woodruff, who's going to talk about attestations. There may be time for a few questions at the end, and if not, William has agreed to maybe answer a few out in the hall afterwards. So let's have a round of applause here for William Woodruff. Here.
Thank you. All right. Hello, everybody, and welcome to the session. So, yeah, the name of this talk is Attestations, a new generation of signatures on PyPI. My name is William, and I work at a company called Trail of Bits. Just a little bit quickly about the company and myself. So I'm currently the open source group engineering director there. My team does a bunch of sort of long-term open source contributions. We're pretty well known for doing things on the Python packaging side of things, but we also do a lot of stuff in the Rust and Ruby worlds. And then outside of work for myself, I'm also a sort of long-term open source person, one of the maintainers of Homebrew, as well as some of my own projects. About Trail of Bits itself, we're about a 130-person R&D firm headquartered in New York, but 80% remote. And then we have all the specialties listed there, too much sort of to say out loud. And finally, a personal note, I tend to speak kind of fast, so if at any point my pace is too fast, please just someone raise your hand and I'll try to slow down. So thank you. Okay, before I get into the details of this talk, I wanted to issue some thank yous to some folks who are in this crowd, some who aren't. As with a lot of the work we've done before at Trail of Bits, this work was funded by Google's open source security team, Ghost. So I wanted to give a special thanks to Dustin Ingram and Hayden Blosvern, both of whom have motivated this work over years and have provided both the technical and financial backing for it. So thank you to both of you. I also want to provide an additional set of thanks to E, Mike, Donald, and Dustin as the PyPI admins and maintainers for their code and pep reviews for this work, and also for not skinning us when we broke PyPI for a couple hours. And then finally, last but not least, my actual team at Trail of Bits who worked on this, and with special thanks to Facundo and Alexis, who are instrumental in this work. So to dive a bit into things, I want to set up an agenda. So first I want to motivate this a bit. Like, do we even have a problem here? Why do we need to even think about attestation, signatures, that sort of stuff? Once I motivate that, I'll dive a little bit into like the technical background of digital signatures, code signing as an example of digital signatures, why this stuff is so hard in practice, why it's so hard to operationalize, and why in practice we've seen most open source signing schemes fail. Take those lessons in failure and use them to motivate a new set of designs, which ended up being what we call PEP 740 and ultimately implemented on PyPI last year. We'll then talk about the outcomes of that implementation, where things are currently in the ecosystem, where we think they can go, where the sort of sharp points still are, and basically how we can get them closer to you as end users. So to start, I'd like to motivate things a bit. So like you might ask yourself reasonably, I think, like, do we even have a problem that necessitates something like code signatures or attestations? And on first glance, Python packaging looks very healthy. There's a huge, vibrant community of maintainers, a large set of projects, a lot of activity, and underpinning all of that is a lot of sort of slow, steady, incremental, what I consider foundational security improvements to the index that should increase the overall trust of users in the quality of the packages they receive. So things that have occurred over the years include multi-factor, scoped API tokens, trusted publishing, and then finally we locked in mandatory MFA, and then more recently things like project quarantine and archival. And so you might reasonably think, like, what is even left to do? Like, we're in a pretty good state now. But like there's this whole world of sort of supply chain security that's popped up over the last few years that adds this sort of new dimension of complexity where on top of the guarantees that the index can give you, you're now worried about this multi-dimensional layer or like cake of dependencies you have of unknown provenance and quality. And so PyPI is like a double-edged sword. It gives you all these like amazing security features at the index level, and in doing so, it makes it super easy to consume arbitrary code from the internet. That's at least how I like to think about it. And so, another way to say that is that security improvements like MFA make the user-to-index protection dimension of the security problem stronger, but they don't address separate other dimensions of sort of risk, things like user-to-user risk and index-to-user risk. User-to-user risks being things like, takeover risks, things like the XZ utils attack that happened about a year and a half ago, as well as things like typo and soft squatting. And then finally, there's like index-to-user risk, where even if the publisher is perfectly secure in their practices, someone who compromises PyPI itself could get away with a great deal. And so we want to reduce the amount of damage that PyPI itself could cause as a trusted party in the packaging scheme. And to motivate this, of course, you'll notice that I asked some LLM to hallucinate some stuff from me, and it generated a perfectly reasonable set of Python packages, except for one, which Google-crc32 does not exist. And so, of course, if you're a more junior engineer who's just trying to get something to work, you might, and perfectly reasonably, hallucinate your way into arbitrary code execution by an attacker. So, to sort of summarize that all together, our goal here is to improve the user-to-user and index-to-user aspects of Python packaging without degrading the things that make open source, and specifically the Python packaging system, ecosystem, awesome. And as sub-goals of that, following from that, it should be harder for an attacker to impersonate or take over a project, and it should also be harder for an attacker to compromise PyPI itself, such that the average user doesn't or can't detect malicious changes. So perhaps the attacker can still do it, but in doing so, they force themselves into the open. And if you're like me, this sounds like a problem for signatures. So let's talk a bit about that. I want to do a quick, sort of scan through of public key cryptography. So the main thing to understand here is that with public key cryptography, which is the thing we use to build signatures, key materials come in asymmetric pairs. You have a private half, which you must keep secret, and you have a public half, which you distribute somewhere publicly so that people can verify against your private half. This is the fundamental asymmetry. One half performs one operation, the other half performs the other operation, and they don't mix. And then digital signature schemes are what we call instantiations of public key cryptography. So you have a signing party, you have a verifying party. These are Alice and Bob conventionally. The signing party does this sign function with its private key and a message that produces S, a signature. The verifying party does a verify function with the public half of that private key, the message, and it produces a proof. And the proof is typically a Boolean that says it passes or fails. And so this proof, if you trust it, establishes authenticity, as in truly this message is from Alice, and integrity, meaning that the message has not been modified since Alice produced it. And then the corollary to this is that the verifying party can establish any signature that they have the corresponding input for. And there's some malleability there, but it doesn't really matter for our purposes. So the TLDR is that a true proof convinces Bob that Alice is the origin of M. Then from there, to extend it a bit, code signing is just an instantiation of digital signatures. It really is just digital signatures, but for code. So instead of the message being a picture of a cat, it's a program instead. And integrity becomes the program wasn't modified before I ran it, and authenticity becomes the program was produced or conveyed by someone I trust, that being Alice or Alice's GitHub Actions workflow, or et cetera. And so, again, to rephrase, if Bob trusts Alice to sign for package foo, then neither an attacker who compromises PyPI nor, rather compromises the project on PyPI, nor PyPI itself can deliver a modified foo without Bob noticing, right? Problem solved. Seems like we can all not think about this anymore. But unfortunately, not so fast. This kind of traditional signing scheme where you have a standard public-private key pair and you distribute the public key comes with a variety of what I think of as onerous assumptions that basically, in practice, make deployment, large-scale deployment, impossible for open source schemes. So the biggest and most prominent one of these is secure distribution. So it's very difficult for Alice to give her public key to Bob without an intermediate party, we'll call them Mallory, someone who gets onto the index, distributing their key instead. So in reality, what we really need is a trusted party in the middle that can distribute Alice's public key. But how do we trust that party? Well, to trust that party, we'd ideally verify a signature from them, and now we need to get a public key for that trusted party, and we have infinite regress. So that's not so good. There's also this timely revocation issue, which is that if instead of replacing Alice's key, Mallory instead steals Alice's private key, Alice must be able to revoke it such that Bob and others distrust it in a reasonable time frame. And then, as a corollary to that, Mallory must not be able to countermand that revocation. But in reality, this is very difficult to operationalize, and in practice, even large, very well-capitalized ecosystems like the Web PKI fail to do so. And then finally, you have this informed expert user problem, which I think is frankly unreasonable to expect the average Python developer. Most of you are experts on everything else but cryptography, and you shouldn't have to learn an entire complicated field to get the benefits of cryptography. I certainly shouldn't have to. And so knowing how to generate and secure a key pair for an indefinite period of time is in my mind an unreasonable thing to expect users to do. And PyPI once had PHP support. This support, I think, in my opinion, embodied many of these problems. The promise was that you could upload your ASC file, your signature, to PyPI, and then a user would verify it against their key ring. The reality is that that key would be of a huge variety of types and sizes and qualities, meaning that it's very difficult to establish a baseline quality for the signature, whether or not you should trust it. And in reality, people would just upload all kinds of junk in their ASC files. And then finally, the promise on the verifier side was that, oh, you have a key ring locally, which you would establish via a web of trust or similar, and you would just verify the authenticity and integrity that way. But in reality, this punts key distribution to the user, who again shouldn't have to know these things, and in reality was never actually adopted all that widely by installers because it requires a functional GPG installation locally. So the outcome was that in reality, only a tiny minority of package maintainers produced these, and so in effect they were defunct. So let's talk about a new approach that doesn't have these kind of problems. So just to sort of rephrase and revisit these received assumptions or received wisdoms in code signing. One of the first assumption, which I think is a pretty big one, is that both humans and computers verify through public keys. And the reality is that this is true, but another way to say it would be that computers verify through keys, but humans only care about the identity bound to the key. So in reality, I don't really care which key belongs to Alice as long as I can be convinced that some key that belongs to Alice is present. That's, I think, an important building block for thinking about a better design here. Another assumption is that humans are at least acceptably good at long-term secret management. In reality, this is not true. Humans are terrible at long-term secret management. Entire corporate teams and industries struggle to do it. I don't think we should expect people doing this for fun to do it. It's not fair to them. Another assumption, users understand basic cryptography. They can generate secure keys, use secure algorithms, et cetera. And the reality is they might, but they shouldn't have to. It's, again, I think not reasonable to expect users to become experts to get security. Security should come by default. And then last but not least, I think, in fact, mostly perhaps the most important, is that there's an acceptable usability tax that comes with signatures. We can expect users to degrade the quality of their experience a little bit in exchange for a bit of security. And I believe this is just completely wrong. I believe that end usability is really the only thing that matters. And that the only way we can get this into end users' hands is to make it equivalent to their existing user experience or better. And therefore, good security design here means defaultable, unintrusive design. So let's talk a little bit about the identity and not key approach. So there's this fundamental impedance mismatch. You have keys, which are what cryptography cares about, and then assigning identities, which are what humans care about, meaning Alice. So our goal with this new design is to collapse that distinction. Instead of a weak identity claim, such as I promise that I am Bill from Microsoft, we want a strong binding, a provable binding between a proven silent identity and its key. This requires a new party within our scheme. This requires an identity provider that can produce publicly verifiable proofs of identity, and I'll get into that in a bit. And in fact, we want to go a little bit beyond that. We want no long-lived keys at all. This goes back to the assumption that users can safely hold keys for a long period of time, which is not true. Holding keys for a long period of time is very easy to do wrong. It's easy to accidentally leak, destroy, or normalize the deviance of your behavior until everything seems okay until a point of catastrophic failure. And so this diagram is with apologies to Diane Vaughn, who produced a much better version of it that I've adapted. And so the idea here is that we want to design a scheme where you cannot normalize your deviancy. You can't do the wrong thing. You're baked away from it. And so that means having short-lived keys that can't be used over long periods of time, that can't be forgotten to be revoked, or can't be forgotten to be expired, or can't be left weak until it's too late and a major security incident happens. Finally, or not finally, another thing that we want to think about for a new approach is revisiting the assumption that bare signatures are an acceptable approach. And another piece of context here is that a typical way to do PGP-based signing is to take the bytes of the program that you're going to sign over and then perform a hash transformation on them, or just do whatever you want to turn them into something collapsible, and then sign over that. And the problem with this is that it leaves parts of the domain unbound to the signature. And so what you really want is you want to say, I know that this distribution name is associated with this set of bytes. You don't want to know, oh, Alice produced a set of bytes, but I don't know which name and version Alice intended it to be for, because then someone can mix and match versions with you. And another way to put that is what we really want is not a bare signature, but an attestation, which is a machine-readable statement that can be verified like a normal message, but additionally interpreted for more domain confabulation, or domain binding, rather. So just to walk through a bit of what that actually looks like, because I think that can be a little bit hard to understand. So let's say, like, you're looking at a PEP 503 or PEP 691 index response, and the index, and the equivalent of an English sentence claims, like, the distribution named sample project 40 corresponds to this digest. And so if we had a signature for this, the question is, what parts of this does the signature actually bind over? Or in other words, what parts can the index or another party lie about? And the answer is that with a bare signature, the signature only binds the digest part. It doesn't bind any other part of that statement. So here, you read it and you do the sign over it. But what that means is that the index or another party can mix and match parts of the domain together. By contrast, with an attestation, the index can make that same claim. However, the attestation binds both parts of the statement together into a single verifiable package. And so that means the index cannot mix and match without the verifier catching them. But a thing to note here is that this is just 2 domains that I've bound together. There's always infinite numbers of other domains. Like what if you have mirrors? You want to say which mirror a package comes from. So that's something to think about in design. And the question is, how flexible do you want to be versus how inflexible? Okay, that was a lot. Now I want to talk about the actual implementation and PEP 740. So PEP 740 is our approach to all these things. I think it adequately addresses all of these design points that I've mentioned. And I want to talk a bit about its internals. So I think the first thing to note that covers a great deal of ground is that PEP 740 is built on top of SigStore. SigStore is a Linux Foundation project that does a lot of the new parties that we've introduced for us under the hood. It provides this identities over keys approach via this underlying certificate log or certificate CA called, or PKI CA called Fulcio, which takes an OpenID Connect proof of identity and binds it to a certificate that contains that identity with a short-lived public key. So that gives us that short-lived and identity binding property that we really want. It also gives us keyless signing because instead of having these long-lived certificates with long-lived public keys, we can do a reissuance every time we want to sign something new. So we get 10-minute long signing certificates by default, which is really nice. It means we don't have to do revocation. But then, of course, this leaves open the question of which identities to trust. So the next big part of PEP 740 that I think is the peanut butter to the chocolate is that PEP 740 is built on top of trusted publishing. Trusted publishing was added to PyPI in around 2022, I believe. It's essentially PyPI's no-credential authentication scheme. It uses the same underlying technology, OpenID Connect, and it allows a verifiable identity, such as a GitHub Actions workflow, to request a short-lived publishing token. And so the nice thing about this technology, or this technique, is that it eliminates 2 big issues with long-lived credentials. One, it automatically scopes the credential for the user, and 2, it expires the credential after a reasonable window of time. So the user isn't able to make mistakes at all. The system heals for itself. And PEP 740, or rather, trusted publishing supports GitHub, GitLab, Google Cloud, and active status publishers, and adding other ones is relatively simple, but requires, currently as a matter of policy, some evidence of widespread use. And the cool thing about this under the hood is that fundamentally trusted publishing establishes a machine identity, and we can reuse that identity for signing. It establishes a link of trust between the machine identity and PyPI, which PyPI can then use to verify attestations. And so speaking of attestations, the last, I think, big piece that PEP 740 is built on is it's built on top of InToto. And InToto is a framework for defining machine-readable attestations, which solves the bare signature problem for us. It allows us to define what we added with PEP 740, which is the publish attestation, which we then sign over. And so that's what a publish attestation looks like. It is, as I mentioned before, a binding of 2 domains, the content domain with the identity domain being the distribution inversion. Which, yeah, that's what that is. So just to tie that all together, SigStore is what gives us that misuse-resistant identity-based signing component. InToto gives us structured machine-readable attestations, and then finally, trusted publishing ties them both together and gives us that pre-established trust relationship between PyPI and a source repository, or rather, machine identity. One that's already used by default, and that we can use to verify on upload. So it allows the index to actually verify attestations as they get uploaded, preventing the quality issue that we saw with PGP. So combined, these, in my opinion, dispel the traditional onerous assumptions in signing. We're able to do secure distribution via strong identity binding. We're able to add timely revocation by essentially making keys expire within 10 minutes. And finally, users get signing by default because we can bake this directly into the trusted publishing workflow that many projects already use via GitHub Actions and GitLab, CI/CD. And then finally, index verification itself provides a quality and signal baseline, which is not a substitute for end user signing, but provides basically a baseline for the ecosystem. Okay, with that, I only have about 10 minutes left, so I'm going to skip the demo, but I'm happy to show people in the hallway or something like that. So with that, I want to talk a little bit more where we are today. So to do that, I want to do a quick recap. I gave a talk 2 years ago at PyCon, basically laying out how I thought this was going to look 2 years ago. And the answer is that, like, it kind of looks like what I said. It's a little bit sketchy. It's a little bit more of a sketch back then. And that's where we are now. And the good news is that as of last November and rolling forwards, because we've been adding features since then, everything that I laid out 2 years ago is implemented. So PEP 740 has been fully specified, approved by the community, and implemented on PyPI. We completed the MVP last November, but we've been adding features and support for new trusted publishing providers ever since. One of the really cool things about this is that at the same time that we enabled attestations, we also enabled them by default in GitHub Action PyPI Publish, meaning that everybody who uses GitHub Action PyPI Publish gets attestations by default when they upload. Which that is all it does. That's all you need on the top right. And the docs for the action will show you that as well. And it's also available, but it's not the default yet for GitLab and Google Cloud Build. And then finally, PyPI verifies and presents these attestations as part of the file details page on each uploaded distribution. So you can see it on the right-hand side. And the really cool thing about this is that this gives you that verified source provenance back to the identity, the machine identity, the repository that produced the build. And it also gives you links to the transparency log. So you can actually check the exact times at which a thing was included in the log, which gives you a proxy for when that thing was built. So again, going deeper into like auditability and transparency. But if that itself doesn't interest you, here's some raw numbers, which I think are pretty impressive. So 14% of all packages uploaded since the MVP have been created with attestations. I think this is pretty awesome, 1 out of every 7. And the overall trend is accelerating. We're seeing it go up over time as people roll onto trusted publishing and upgrade their workflows to ones that sign by default. But even more impressively, in my opinion, is that over 1 in 5 of the top downloaded packages, top 360 packages, have attestations already. And I think this is a really marked contrast to PGP signing, where at its peak it had about 4% adoption, and then before it was officially deprecated, it went down to 0.3. So I think we've successfully demonstrated a volume that PGP failed to on PyPI. Okay. Another thing I want to highlight as a big part of where we are currently is the auditability and auditing and discoverability wins that come with this. So I mentioned that transparency log entry before. This log entry and the other transparency components of the scheme make incident response way easier than it used to be. And I think a good example of this is the Ultralytics incident that happened back in November, or December. And in that incident, we saw that the attacker did in fact produce an attestation, and in doing so, they forced themselves into the open, meaning that we were able to establish a precise timeline for when they took over the repository. This, in my opinion, is a huge win, because previously that would take someone who's an experienced incident responder a few hours to untangle via the various sources, because you'd have the exact times on the PyPI side, but not necessarily on the source repository side. So in my mind, that's a huge win. And there's a really great post by Seth on the PyPI blog about how that went down. So I recommend checking that out. Okay, and then sort of last but not least, to put a damper on things, where we are now is that manual end user verification is the default, rather. So we have signing, we have index side verification, but at the moment, in order to verify attestations locally, meaning not trust the index to do it, you need to run a command manually. You can't trust pip or UV, or rather you can't expect pip or UV to do it for you. So if you are feeling brave and you want to try this out for yourself, we have a package called PyPI Attestations, which provides both a library and an experimental CLI, and you can use that to verify attestations locally. However, as you can tell, that is not exactly a pretty thing to write in your terminal. It's pretty long, so I would not necessarily recommend that unless you're experimenting, and I'll go into more of how we want to get to a better place in the future. So with that, where next? The big thing, which I guess I foreshadowed, is we really want default end user verification. And this comes with a bit of a hard truth, which is that the impact of any signing scheme, no matter how good your primitives are, or no matter how default it is pretty marginal until you have really pervasive, wide breadths of verifying parties. So ideally, not just the index itself, but also lots of verifying parties, companies, individual users, et cetera, verifying these attestations. So in our case, we get PyPI as the baseline one, which I think is great and is already a significant improvement over PGP, but we can do a lot better, in my opinion. And so our real goal is to get verification into users' hands by default. And the answer is that we're kind of getting there, in my opinion. Just a month or two ago, PEP 751 was accepted and has already been adopted in quite a few packaging tools. And the cool thing about this is that I no longer have to dream about what lock files would look like in the Python ecosystem. It is happening. And PEP 751 includes components within it that allow us to lock attestations within lock files, which means that in the future, tools that support attestations will be able to check whether an identity diverges between releases, allowing you to detect, for example, if someone tries to remove their signatures, downgrade or change identities, as in take over the project. That is where I see this feature going. Or another way to put that would be that PEP 751 gives us the building blocks for what's called a trust on first use, or TOFU scheme. A user would do a pip lock or similar to initialize their lock file. This would bake those identities into the lock file. And then on upgrades, the upgrading tool, the installer, consults the lock file for locked identities. And then those are verified. This satisfies the goal at the cost of it being a trust on first use scheme, meaning that there is still a fundamental initial trust phase, but with auditability and transparency, we believe that that is a relatively acceptable cost in exchange for default verification on end user machines. Okay. A little bit further out, something that I've been thinking a lot about and I think is really important in these kind of schemes is monitoring. So one thing I've talked about a lot is transparency. And transparency is really great, but it's really at its best when it's used automatically in a monitoring scheme. So what we want to do is trivial monitoring for end users. If you are a maintainer of a package, you should be able to list your package's identity, foo package on PyPI, and get alerts that are cryptographically verifiable when someone else publishes to your package namespace or your identity. And so the goal here is something that resembles CertSpotter for TLS or GopherWatch for Go, but for Python. I think that's really where this kind of feature should go. So I'm going to wrap it up. Some final takeaways. Defaults matter. PEP 740 works versus historical approaches to code signing in Python because it notches into existing workflows by default. And the corollary to this is that defaults need to be unintrusive, especially in long-tail ecosystems like Python, where you have hundreds of thousands of packages that don't update just because you want them to. Getting to a default-ready state here, as another corollary to this, took years of incremental changes. We needed to first crawl, walk, and run with things like API tokens and trusted publishing to get to a place where we could even think about doing signing this way. Another big takeaway here is that trust is unavoidable. PEP 740 does a little bit of like shuffling of trust, but fundamentally doesn't remove trusted parties from the scheme. All it does is make them more explicit and makes them more transparent. So what we really want to do, if we can't remove trust, is use technologies that allow us to substantiate it instead. So that means making the new parties, OIDC providers and the PKI within SigStore, accountable to us via transparency. Or, to put it more bluntly, we cribbed the basic idea behind the Web PKI's transparency scheme and put it into the Python ecosystem, because that has been known and proven to work at a much larger scale than Python packaging. And then finally, a big takeaway here, and again, to hammer home this is not done yet, is that signing is the easy part. There's a really long way to go in terms of default end user verification. Index verification is good, but it's by no means enough. And we need a sort of broader set of verifiers to gain increased trust in the ecosystem. So PEP 751 is a key part of that, will get us close, but it is still a long road. We still need to actually have lock file generators, embed identities for the tofu part, and then installers and updaters need to consult those locked identities when doing their upgrade phase. And then last but not least, and actually pretty importantly, users need to actually understand what's happening when that is going on. And in my opinion, this is easier for them to understand than opaque key identifiers changing over time, or keys expiring randomly, or their key ring being corrupt. But it's still difficult to understand why a change in just a workflow name on a trusted publisher does or doesn't reflect a change in your security posture. And that is a hard problem to solve from a sort of documentation and user legibility perspective. That's everything. Thank you very much for coming to my talk, and I hope it was interesting.
Yes, Israel!
We have time, I guess, for just a few questions. If anybody has one, come to one of the mics.
Do you have any thoughts on how, when a repository moves, for example, that sort of situation would be handled so that, the projects don't just get hammered by requests when things start changing?
Yeah, that's a great question. So the underlying problem here is, let's say you want to move your repository to a new org or choose a new name. And under this scheme, when that rename change occurs, that's also an identity change, meaning that it's the equivalent of a key rotating. And so there's a couple ideas that we have for this. One of them is that GitHub itself lets you know when a redirect has been done in a trustworthy manner. And so if we know that redirect was done on GitHub's side, we can sort of infer that it was a trustworthy identity change. You can just update those identities. And then when you can't infer that, that is in fact a good positive signal for exploitation.
So everything you've shown is fantastic for user verifying the source code if what they're downloading is the source code is published. What happens in the presence of wheels?
Yes, great question. So I didn't go into too much detail in this talk, but we're very careful about what kind of attestation we produce. We do not produce a source attestation. We produce what we call a publish attestation. And a publish attestation is only a proof that a given distribution was uploaded to a given index. And so we do include wheels in that because we are not asserting the provenance of a wheel. We are only asserting that it came from a trusted publishing source. So the short answer is that we sort of collapse the distinction for these attestations. However, you can also upload salsa attestations to the index, and that would be that's SDIST only. Yep.
All right, let's have a big hand once more for William.